we're going to think a bit about Kepler's third law of planetary motion, the harmonic law, and in simple form it's telling us that p squared is a cubed. The orbital period measured in years squared is the semi-major axis measured in astronomical units cubed. So Kepler's third law describes the relationship between how long it takes a planet to orbit a star, the orbital period, and how far away that planet is from the star, orbital distance. In this activity, we investigate an imaginary planetary system that has an average star like the Sun at the center and two planets. A huge Jupiter-like Jovian planet named Isis orbits close to the star, while a small Earth-like terrestrial planet named Solus is in orbit far away around the star. Use this information when answering the next four questions. If you're not sure the correct answers to questions 1 through 4, just take a guess. We'll return to these questions later in this activity. So which of the two planets, Isis or Solus, do you think will move around the central star in the least amount of time? Explain your reasoning. Sorry, I'm going ahead because I remember what Kepler's third law is. So Isis has the shorter period because it has smaller semi-major axis. So, if Isis and Solus were to switch positions, would your answer to question 1 change? If so, how? If not, why not? No, my answer would not change because I just have a relationship between period and semi-major axis as long as we're orbiting the Sun. Do you think the orbital period for Isis would increase, decrease, or stay the same if its mass were increased? Well, I just have a relationship between period and semi-major axis. It doesn't have the mass of Isis in it. So it's going to stay the same. Imagine both Isis and Solus were in orbit around the same central star at the same distance, and that their orbital positions would never intersect, so that they would never collide. Which of the two planets, Isis or Solus, do you think will move around the central star in the least amount of time? Explain your reasoning. So which in the least amount of time? Neither. Because they move the same time. Period squared is a cubed. If they're in the same orbit, they have the same semi-major axis, therefore they have the same period. Okay? These statements are true because the mass of a planet, even Isis, a Jovian type planet, that mass is tiny compared to the mass of the Sun. Alright, we have a graph. That graph illustrates how the orbital period expressed in years and orbital distance expressed in astronomical units of a planet are related. According to the graph, would you say that the orbital period of planets appears to increase, decrease, or stay the same as their orbital distance is increased? So if I go further along the x-axis, the curve is going up. So as the semi-major axis gets bigger, the period gets bigger. How far from the central star does a planet orbit if it has an orbital period of 1 year? So orbital period of 1 year intersects the curve and an orbital distance of 1 AU. So 1 astronomical unit. How long does it take a planet to complete one orbit if it is twice the distance from the central star is the planet described in question 6? So I go to an orbital distance of 2. The orbital period, so there's 1 year, 2 years, about 2 2/3 years. Based on your results from questions 6 and 7, which of the following best describes how a planet's orbital period will change, if at all, when the distance to the central star is doubled? Circle your choice. The planet's orbital period will decrease by half. Well, no, it increases. The planet's orbital period will not change. No, it increases. Increases a change. The planet's orbital period will double. Well, I doubled A, but it's not 2 years. It's even bigger than that. The planet's orbital period will more than double. Okay, here's some data for our own solar system. In the table below, we have provided the orbital distances, orbital period, and masses for the 6 planets closest to the Sun. So we have orbital distance in astronomical units, AU, so this is semi-major axis A. Orbital period in years, so that's orbital period P. And planet mass in units of Earth's mass. So 0.06, 0.82, 1, 0.11, 318. Big old Jupiter. 95.2, Saturn. What is the name of the planet that you identified the orbital distance for in question 6? So 1 AU for A gives me 1 year for P. So that planet is home sweet home, Earth. Using the information provided in the table above and on the graph in the previous page, which of the answers below best describes how a planet's mass will affect its orbital period? Circle your choice. So the plot on the previous page showed how period squared changes as A cubed. So I plotted P squared versus A cubed. That would be a straight line. If I plotted it as just P versus A, there's a curve upwards. So let's go through our choices. Planets that have small mass have longer orbital periods than planets with large masses. No, that's pretty clearly not true. Planets with the same mass will also have the same orbital period. Well, 0.82 is pretty close to 1. The orbital periods are not necessarily close or that close. I don't think that's supported by the data. Planets that have large masses have longer orbital periods than planets with small masses. Well, the two big guys do have big orbital periods, but Mars has less mass than Earth, and Mars has a greater orbital period than Earth. You look at the trend with mass and how orbital period is changing. I think the conclusion you come to is the orbit of a planet does not depend on mass. We have a student in class has the following thoughts about the relationship between the location of planets in our solar system and their orbital period and mass. Student. As we look at planets farther away from the Sun than Mercury, we see that their distances get bigger, and that the mass of the planets is also getting bigger, larger. So I think that the farther away a planet is from the Sun, the more massive it will be, and the longer it will take to go around the Sun. Which planet in the table above illustrates the fact that the student's reasoning is incorrect? Explain your reasoning. So we had talked about Mars is breaking that trend, as less mass than Earth and Venus, and then also to a lesser extent, Saturn has less mass than Jupiter. All right, review your answers to questions 1 through 4. Do you still agree with the answers you provided? If not, describe how you would change the answers you gave initially. So that's on you, but simple form of Kepler's third law for objects orbiting in the solar system, they are all tiny compared to the mass of the sun. They just have a relationship between period and semi-major axis, and there is no other variable in there. That's it.